Today's lesson is on ice tables. Specifically, we're going to be looking at problems dealing with the pH of weak acids. So how do we calculate the pH of a weak acid if we are given a Ka and a molarity of that acid? So we are going to start with example 1 here. Remember, these are only weak acids. Strong acids behave differently. So it'll come in handy to have that list of strong acids nearby as we're working through these types of problems. Today, we're solely focusing on weak acid dissociation. So you won't see any bases here for these reactions, only weak acids. And we're only going to deal with finding pH today from Ka. That can go the other direction, but right now we're focusing on one step at a time. So example 1, find the pH of a 0.35 molar solution of benzoic acid. And we're given the Ka for benzoic acid at these conditions to be 6.3 times 10 to the negative fifth power. Okay, remember that I mentioned before that K is temperature dependent. So that's has to be given to us for this particular situation. So the first thing we're going to do, okay, for one of these problems is write a dissociation reaction. So if you don't know what benzoic acid is, we look it up, right? So it's HC7H3O2. We know it's aqueous because we're creating a solution. You could put plus H2O if you wanted to and show the dissociation and show hydronium here rather than H+. I personally prefer the H+. Because I like to take the path of least resistance, and that's faster for me, and I like to see that proton in my reaction. So that's just preference for me. Both ways are correct. Okay, so we see that we have dissociated our benzoic acid into a proton and the anion, right? So our next step is to create something called an ice table. Okay, this is a mathematical method in order to set up an expression to solve for x. Okay, so it's called an ICE table, ICE. So the I stands for initial, N-I-T-I-A-L. So the initial concentration in the problem of the benzoic acid given to us is 0.35. So I'm going to record that here in the initial part of our table, 0.35 molarity. We're all going to be in molarity dealing with concentration, so we don't actually have to show that unit there. It's understood that we're dealing with that same unit throughout our ice tables. Okay. Now, initially, when we create the solution, we have 0.35 molar concentration of the acid, and we have 0 of the proton and 0 of the anion. Why? Well, because we haven't formed it yet. We just started the reaction, so that's the point of the initial part. The next step, we have what's called the change. Okay. And for the change, that's where we know we're going to get a difference. The reaction's happening. That 0.35 molar is going to change because the benzoic acid is going to dissociate. Now, remember, these are equilibrium arrows. That shows this exists at equilibrium. So the reaction is going to proceed toward the right to form more products and proceed back toward the left to form more reactants until it reaches a state of dynamic equilibrium, which means that the forward and reverse reactions are occurring at equal rates. Essentially means it gets to a state where the concentrations are pretty much not going to change anymore, okay, without an additional stress being added to this reaction. So we're going to get a change. Okay, what's going to change? We don't know. That's what we've got to figure out. So we know that we are going to change by subtracting some amount from 0.35. We're going to call that amount x. Okay. We know that we are going to form some H+. We're going to call that plus x. We know we're going to form some C7H3O2 negative. We're going to call that plus x. Now, it could be 2x, it could be 3x. The reason these are all 1x is because we are at a 1-to-1-to-1 ratio. 1-to-1-to-1 mole ratio. So remember back to balancing equations, right? So we don't see any balancing that had to occur here. And since we're at a 1-to-1 ratio, we can just subtract and add a single x to each one. Okay. Now, if this had been 2 protons here, for example, instead of 1, it wouldn't be. But if it had been, we would have to add 2x to that rather than just adding x. All right. So that's going to be our change. So that's going to give us, for our E stands for equilibrium. So our equilibrium concentrations are going to be different than our initial. So our equilibrium concentration is 0.35 minus X. Okay, well, that makes sense, right? All right, and this one is going to be, well, about X. And then this one's going to be approximately X. Okay, so for our next step, we are going to write a Ka expression, which you guys have already been doing. So we know that a Ka expression for an acid in general is our products over reactant. So it's going to be H plus for this particular reaction times the concentration of C7H3O2 negative divided by the concentration of HC7H3O2. Okay, so now we're going to plug numbers in. So we know that that should be equal to, well, our H plus concentration is X from our chart here. Our C7H3O2 negative concentration is also X from our chart here. Okay, and then on the bottom, our HC7H3O2 is 0.35 minus X. Now, for these early on problems, we'll talk about why a little later, but for these early on problems, we're going to neglect the subtraction of X. Why? There's something called the 5% rule. It makes less than a 5% difference in the final answer when we subtract X because we're looking at such tiny values. So we get into numbers like 0.000000345. And if we subtracted X, we might get something like 0.000000346. Okay, so we're talking about tiny changes. So we're going to neglect the subtraction of X for these problems because it simplifies our math significantly, makes a faster process for us, and we get pretty much the same answer anyway. Okay, so I'm going to move this on to the next step mathematically. So what we get next is our Ka value is given to us in the problem, so we're going to substitute that in. Okay. So our Ka is 6.3 times 10 to the negative fifth. Okay, so there's our Ka right there is equal to X squared over 0.35 for this particular problem. So we were going to, in order to solve this, we're going to multiply both sides by 0.35. Once we do that, we'll get something like, let's rewrite that for you. So we get X squared is equal to 0.35 times 6.3 times 10 to the negative fifth. So we're going to take the square roots of both sides. We get X is equal to 4.7 times 10 to the negative 3 molarity. Just remember, X was the change in concentration that we saw above. Okay. Now, final step, we were asked to find pH. You know that pH is equal to the negative log of the hydrogen ion concentration. Okay. Well, our H plus concentration at equilibrium, so our H plus, I'm going to call it EQ here, just to be specific for you, is equal to X, which is equal to 4.7 times 10 to the negative 3. Okay, so basically we need to take the negative log of that. Okay, negative log of that. Sorry, my screen's running out here, huh? Let's see if I can make that better for you. Yeah, let's try that again. All right, so let me rewrite that. So pH, negative log of the H plus. We know that H plus is equal to X, which in this problem we just solved for and found X to be 4.7 times 10 to the negative 3. Okay. So now if we take the negative log of 4.7 times 10 to the negative 3, we are going to get a pH of 2.33 equals pH, just so we're clear. 2.33 equals pH. Okay, let's look at a second example. All right, example 2. Find the pH of a 0.275 molar hypochlorous acid solution. Ka is given to you as 3.0 times 10 to the negative 8. This is exactly the same as the previous example. We're given a different acid and a different Ka. We go about solving in the exact same way. I want to walk you through the setup of this one. So I've got a dissociation reaction. Once again, I did not include water or hydronium. I left that out. So instead, I have just the H plus instead of the H3O plus here. Same thing. Okay. Both of those are fine. Both are correct. All right, so my first step is going to be to set up my ice table. Remember, I is for initial. So our initial concentration of the acid given to us in the problem is 0.275 molar. And our initial concentrations of H plus and ClO negative are 0. Okay, it didn't tell us they were anything, didn't give us any of that information. Other ice tables in the future, we will look at that a little differently. We may not have that. We may have other numbers that go in those places. But for us, initially, we are starting with only this acid. We haven't formed any products yet. So we're starting with concentrations of 0 for those. All right, so now for our change. Once again, we have a 1:1:1 ratio, mole ratio. In this equation, our balanced equation, we don't have any additional numbers there. So we are going to change by a value of X for all of these. So our change here is going to be minus X. Here we are plus X. Here we are plus X. Once again, why are we subtracting on the left and adding on the right? Why is it that way? Well, initially we're starting with a 0.275 molar HClO solution. When we begin to form products, that concentration is going to decrease. Okay, it's got to go down. That's why we are subtracting X, because we know that concentration is going to go down. We know that products are going to form. H plus is going to form, ClO negative is going to form. That's why we use the addition of X on those sides, because we are going to form those products. So that's why those are plus, the other side's minus. Okay, so for our equilibrium part, we now have 0.275 minus X. Here we just have plus X. Here we just have plus X. Pretty simple. Forgive me with the plus. You could leave that off on this side. The positive part's just a habit to show that it's a positive X on my part. Just X is fine. Okay, so our next step is going to be to set up that Ka expression. Right, so Ka for this reaction is equal to the products, our H plus times our ClO negative divided by our HClO concentrations. All right, so let's set that up. So we have Ka is equal to X for H plus. We're going to substitute in X for our ClO negative concentration. On the bottom, we're going to have 0.275 minus X. Okay, and remember for these, I've given you all permission to neglect subtracting X. Okay, so we're going to let that part go now at this point. So that leaves us with our Ka is equal to X squared over 0.275. Let's get us a new page. Okay. So our Ka value given to us, let's write that. Ka is X squared over 0.275. Ka given to us was 3.0 times 10 to the negative 8. That's equal to X squared over 0.275. We're going to multiply both sides by 2.275. Cancel that out. Multiply by 0.275. Okay, we're going to get X squared is equal to, just to be sure we're good on the math here, guys, X squared is equal to the product of 0.275 times 3.0 times 10 to the negative 8. Once you multiply your 0.275 and your 3.0 times 10 to the negative 8, you're going to take the square root of both sides in order to find X. In the calculator, so just take the square root. So we're going to get X is equal to 9.08 times 10 to the negative 5th molarity. Okay, remember that our H plus was equal to X, or H plus EQ, let me be specific. Okay, so the hydrogen ion concentration and at equilibrium was equal to X. So therefore it is equal to 9.08 times 10 to the negative 5th molarity. We know that pH Okay, pH is equal to the negative log of the hydrogen ion concentration. Therefore, our pH is equal to the negative log of 9.08 times 10 to the negative fifth. We solve that, we get our pH is equal to 4.04. Final answer. Okay, that's it for today, guys. Next time we will look at some weak base reactions and what happens when we have strong acids as well. Those problems are solved a little differently. Thanks for listening today.